Well, I'm the artist, I'm the composer, I'm collaborating with Till. And well, we will present Smart SOS. And well, in the very beginning, I have to say, sometimes it needs a very long time for artistic ideas in the context of art and science to come to fruition. In our case, it's 10 years. And we met for the first time 10 years ago in Dresden at the Max Planck Institute for Cell Biology. I was there invited for art residency to explore all the labs, and I explored also the lab of Stefan Dietz, and I met a young PhD student, and this was Till Korten, and he was working on a real fancy experiment, and we made experiments together under the fluorescence microscope, and this is how it looked like on a fluorescence microscope. You see these crazy guys moving around, and the point is, this motion is not, these are not bacteria, this is a level under, this is sub microbiological, because these are fiber molecules of our cells moving there. And well, it looks cool. Some of you were laughing, and it looks interesting. But I had a problem, and it looks cool, but I couldn't create out of artwork because I was missing the artistic surplus. And so it took a long time, and things changed a lot. You changed your research, you developed further research, you went into, even with that stuff, into biocomputing. You will tell in a second about this. And I was moving more from, well, the visual arts more into the sound arts, and I will tell you later about the concept. And so it's up to you to explain a bit about this crazy world of microbiology.
Yes, so basically to explain to you what was going on in that movie. So this is an animation of a molecular motor as it moves inside every one of your cells. So we really have these moving along our nerve fibers and supplying the nerve fibers with materials so that the synapses don't die. And we take these motors out of the cell and make them perform as nanomachines, because that's what biology designed them to be. So just to give you an idea how small they actually are, we have this next slide here. So you can fit as many pinheads into a football stadium. You shouldn't do that now because they want to play soccer there, but in the World Cup. But if you did that, you could fit as many needle heads into the football stadium as you can fit these molecular motors into the head of the needle. So that's how small they are. So they're really nanomachines. They move and really they move like we do with 2 feet. We call them heads, but don't mind about that. And they can perform work. And what we've, since Tim and I first met, what we did was to sort of develop ways to control their motion so that we can make them do useful things. And this is here, what you see here is a network with channels shown in yellow, where we can make these motor proteins move along these channels. And then we have junctions and that encode a certain functionality. And in this case, we have a junction that when they move right, they decide not to add a number. Now, when they turn left, they add that number to the sum that they're currently calculating. And then when they hit the next, second type of junction, we call a pass junction, where they have to move straight. Then they start counting up that number that they're currently summing up. And the exit at which they arrive at the end then corresponds to the number that they've been currently calculating. And by this, we can really make these molecules, we can make them count, we can teach them to count, and we can make them perform mathematical operations. And actually, this type of network solves a problem which is called the subset sum problem, which is a special form of what is called the knapsack problem, which is a problem that is actually used in cryptography and also is an optimization problem. And this we can, so the motor proteins can help us solve these kinds of problems and really make us basically, so we can turn them into a biocomputer that uses a lot less energy than a conventional electronic computer. And so this is what we are doing at the Bio4Com Consortium, where we have this collaboration between Germany, Sweden, Israel, and UK. And with that, basically, I will let Tim, so when Tim came to our lab, we designed, or he designed the structure and challenged us in completely different ways than what we had did before, and we came to this very interesting piece of art.
Well, I guess, and you see the challenge, there's obviously a difference. You see a big circle, and the BF4COM structure is a unidirectional structure. You can imagine it like a marble play. You put in a marble, and it comes out, and then you have the distribution of the marbles. And this is a circular structure using the same type of junctions, but creating a kind of circular, simple network. And the point is, what I wanted to do is a kind of, and this is the acronym for SOS, is self-organizing synthesizer. This is what I want to create with your fascinating technology. And what you need for self-organization is feedback. And so this is, you have the output, and it goes to the left or the right network partner in that network. So we started to design this in September in Dresden Technical University. And so you helped me with simulating all this stuff. Then we had to ask how to get the agents into that structure. So we added this structure. This is a feeding structure. So this is the reservoir for the molecular agents, and form follows function. So you see this circular saw blade structure. This is to keep the agents in the circular motion. And you see this connection to the outer circle. This is where the agents are fed in. And then we went to production to Chemnitz, to the Fraunhofer Institute. And this is a negative, and this is a positive image of this nanostructure. The diameter is just 200 micrometers. This is etched in silicon physically. So we have now the structure. So, and what the artistic approach? Artistic approach is not to do visuals, but to translate this into sound. So in every of these units, I put in a measurement point. So in total, these are 30 measurement points arranged around the circle. And they control 30 speakers pending now in an installation, the activity, and they're flashing up by light, they're playing a sound, and the activity controls also the bass frequency of that speakers. The next question is, well, this is the technical setting, is how to get dynamics now into that system. And one thing is, we played a lot around in simulations, is to play with the connections from the inner reservoir to the outer network ring. So, and by changing the numbers of connectivities, this changed the spatial temporal pattern of the agents moving in the outer circle. And this is the real innovative point, I think, of our collaboration. We created a kind of new logic switch. And that's the logic switch. And this is here from the scanning microscope picture, what you see here. You showed before in the animation the junctions. And this is a modification of the junction, and a very simple one. Normally, you have agents coming from the bottom right going to left top, and from the left bottom to right top. What we added is now this dead end. And the consequence of this dead end is that agents coming from the lower right, they tend to stick into that dead end. And what happens then is they potentially block the path of agents coming from the other direction. So, and if they block it, you raise the possibility to the agent to go into the solution, so they just disappear out of the system, of the computation system. So you have a logical interaction, and that's the principle of a switch. And we tested this switch, and in principle, it really works. And so this is just an impression of a working situation. A lot of computing was included, so you maybe have a few words about our working.
So this is Tim and myself sitting in front of a computer looking at the simulation results. And so this was really where basically Tim helped us create new innovation, because he, as I mentioned before, he challenged us in a completely different way. So normally in our networks, we are very happy that the agents, they don't interact much. And they don't disturb each other, so that they can really work in parallel and do parallel computation. But in this case, Tim wanted us, basically, this was too boring. so to speak. So he needed them to interact. And then we thought, okay, we had these artifacts when they get stuck, sometimes they derail each other. And so Tim and I designed the structure where they purposefully get stuck, and then they get derailed and actually interact with each other. And we're really pursuing this now as a way to design new networks that create new kinds of algorithms and solve different kinds of problems.
Yeah, and well, it was fun to work with you. It was fun to work with your partners in Chemnitz and also in Sweden, Kalmar, and in Lund. And well, this is an impression how it looks like. So it is not only about computation. So at a certain point, you need to get into the hardware. And the structure, as you see here, I produced here for 2 days at Chemnitz. Well, is this tiny chip? I can give you around later on. You can, well, obviously you don't see that much. So you just the top tip of a needles because it's so tiny. And well, this is the structure, but the point is we bring on a kind of life into the structure, and how it looks like you will see in the next slide. And what you hear also is, well, a part of this translation of the activity in that network. So I just stop here because you have the opportunity to see it not only, well, as my simulation from last winter, but really live here in the Studio 5 at ERCAM, running this afternoon and then tomorrow afternoon. And I invite you to visit the show and yes, and to experience this noisy environment. Thank you so very much.
Thank you, team. Thank you.
So.